Okay, good evening to all. Welcome to week 11 of our NPTEL TEA discussion for our course Electrical Machines 2. So, last week we were discussing the concepts of single phase induction motor, and we have arrived at the not so equivalent circuit but almost equivalent circuit for our single phase induction motor. So, we were left with some topics of arriving at the exact equivalent circuit of our single phase induction motor and deriving the torque expression for it. So that's where we have stopped in the last session because of time limitation. So I just want to discuss those topics before proceeding into our this week's discussion so that we will be more clear with the single phase induction motor concept and we will complete it as a whole. Now on the screen we can see the last week's discussion where we have stopped our discussion. So this was the uh, almost approximate equivalent circuit for our single phase induction motor. Here we can see the positive sequence equivalent circuit has been added in series with the negative sequence equivalent circuit since both currents are same, so that we can connect in the yeah. Uh, I think you have to rejoin back because everyone else can hear me, I guess. Just Balaji has confirmed me that he can hear me.
Yes, sir.
Yeah, yeah. So please, yeah, thank you. I think Neeraj, you can just join back once if you could do that. Yeah. So yeah, we were discussing about this, and we came to this idea of joining these two equivalent circuit in series because same current is flowing through each equivalent circuit, that is Im by 2. Now, when we added in series, we have arrived at this particular torque expression TEF minus TEB, that is forward field torque minus backward field torque, and we have arrived at the equation number A. Now, one thing which is bothering us from this equation is if you see the original circuit, which at the bottom of the screen, we can see the original diagram of our single phase induction motor. The current flowing through the circuit in the field winding, that is stator winding, is Im, where the supply is Vm in the main winding. Now, Vm and Im are our original parameters, where in the equivalent circuit we have derived it is Vm, that is okay, that is matching, but the current is half of it. Now, this is the thing that is disturbing us. So then we came to an idea. The last week I was discussing with you about that. What if to make the current double from Im by 2 to Im, what if we half the impedance across all the circuits, across the whole circuit? If we can able to bring the impedance down to half, then we are sure that we can make the current double. So when the resistance goes half, current should go up. So that's the Ohm's law. Now keeping the voltage constant, of course. Now that's the idea. Now taking that as an idea, let's 1 second. Yeah. So taking that as an idea, let's arrive at exact equivalent circuit where we will be halving all our impedance and joining the positive and negative sequence so that the current will be doubled. So now let's see the exact equivalent circuit. I'm drawing it. So this is the old equivalent circuit where the current is Im by 2. Now I'm redrawing the equivalent circuit, making the impedances across whole circuit half so that the current will be doubled. Why are we doing it? To arrive at the original terms of Vm and Im. So yeah, exact equivalent circuit of single phase induction machine. Okay. Now same circuit, I'm just drawing it with the impedances half. So I'm just trying. First, I'm drawing the positive sequence part, which is the forward field. In the forward field, the resistance is this, and the impedance and the reactance this part. And now we will be going through the magnetizing part. and this is the rotor part. Okay. Yeah. If you see, this is R1 by 2. So this is the important point. We are halving the impedance, and this is X1 by 2, and this is JXM by 2, and this is X2 dash by 2, and R2 dash by 2S. Okay, now here we will be giving VM. I will write it at the end because we have another circuit in series with it. Now just I am adding the another circuit in series. Now from here my negative sequence will start R1, X1, and again R magnetizing, and again the reactance, and this is the rotor part. Okay. Now the notations for these are R1 by 2 again, and this is X1 by 2. This is JXN by 2, and this is X2 dash by 2. But the important thing is here, this is not R2 dash by 2S. Since it is a backward field, the slip is 2 minuses. R2 dash by 2 into 2 minus S. Now this is the combination of whole circuit, exact equivalent circuit with supply. The total supply will be same, that is Vm for the total circuit, it's Vm. And now the current is not Im by 2 anymore, but it's Im. And we also discussed the current flowing through this resistances. Have I mentioned it here? Okay, yeah. So here if you see, this is IF1 and this is IB1. Now since Im by 2 is double to Im, now IF1 should also be get double. Okay. Now this is 2 IF1, and the current flowing through the resistance of the rotor is here 2 IF. Sorry, 2 IB1. Okay. Now this is the equivalent circuit of our circuit, which is this kind of machine. Main winding, supply. If this is Vm and this is the current flowing through it, Im, and this is the main winding, and this is the rotor, and this is the stator. And my rotor is rotating with NR, and yeah. Now this is my equivalent circuit. Now we have arrived at an exact equivalent circuit of our single phase induction motor here. So what do you see now? This particular branch is a parallel branch, and then there is R1 R1 by 2 X1 by 2 in series with a parallel branch, and that is in series with this particular R1 by 2 X1 by 2, and that is in series with another parallel branch. So there are two parallel branches and four components in series, R1 by 2 X1 by 2. So these two are in series with these two, and also in series with these two parallel branches. Now what I will do, I will just combine all the resistances here, R1 by 2 plus R1 by 2. Here is our R1 by 2 and this is the R1 by 2. I will add them up because they are in series, and this X1 by 2 and this X1 by 2. I can add those two up. Now we are just trying to simplify this circuit even further to see how exactly our circuit would look like. Now if you see, I'm just trying to simplify it further. R1 by 2 plus R1 by 2, and this is R1. So this one and this one I have added, and then we have X1 by 2 and X1 by 2 gives to X1, and these two I have added, and then I will represent these two parallel branches. Only thing left here. Now I will represent these parallel branches as okay. Now this is this first parallel branch, and where it is R2 dash by 2s, and this one is x2 dash by 2. So these can't be added up because they are inside a parallel circuit. And the bottom one is jxn by 2. And there is another parallel branch, and this is jxn by 2, and this one is these two. Now this parallel branch, this is R2 dash by 2 into 2 minus s, and this is x2 dash by 2. And this is nothing but our final equivalent circuit. And here I am giving a single phase AC supply of uh, VM. Okay, let's write it more like exactly like this one where we are seeing it. Here we are giving our supply, and yeah, this is VM. Okay, and this is the current flowing ion. Okay, now yeah, you have to keep in mind that the currents flowing through the resistive part of our rotors, that is rotor, that is this is to IF, and this is to IB. So that is the negative sequence rotor current that is flowing, and this is the positive sequence rotor current that is flowing. Positive and negative represents the forward and backward fields here. Now, with this as an equivalent circuit, taking this as an equivalent circuit, let's calculate our torque and also, or you can say the air gap R. I mean, if you are calculating torque, if you don't want to add that extra term of 2 pi ns, you can talk about torque in terms of synchronous watts. If it is a synchronous watts, the expressions for both torque in synchronous watts and also the air gap hour will be same that we have discussed a few weeks before. Now, yeah, so this is for a single phase induction machine, and we have seen the torque expression is here. We can see torque is TF minus TEP, that for that circuit. And if you see 2 times of IF1 square R2 by S, because this is for a two-phase machine, this is individually have written. Now, this is no longer a two-phase machine now. It's a single-phase machine where there is only one winding, main winding, and if you calculate the torque for it, torque net, it's in synchronous watts. That's why I'm not writing any term of 2 pi ns in front. It will be same as air gap power also. So it will be in watts. It's in synchronous watts. Now, okay, the formula will be there is no multiplication factor of 3I2 square R or 2I2 square R. It's not any phases anymore. It's for a single phase. That's why there is no need to multiply anything. We'll just write the expression. Now, first parallel branch, current flowing through the rotor. We have to take the resistance part square, R2 dash by 2s square. Sorry, R2 dash by 2s multiplied by current square. That is I square R. The current flowing through this branch is 2IF multiplied by R2 dash by 2s minus net torque. So the current flowing through this will be 2IB square multiplied by R2 dash by 2 into 2 minus s. Okay. Now, if you see, we can just bring the equation. If you want to simplify it further, the 2 comes out of the equation, 2 square 4, and 2 will be get cancelled out. And what we can write? Now, we can write it as 2 into R2 dash by S into IF square minus, here 2 square 4, here again the 2 is in the denominator, 2 into R2 dash by 2 minus S into IB square. This is T net in synchronous Now, this is the equation B, which we were talking about in the last week, where we will arrive at the equivalent, exact equivalent circuit of our single phase, and we will be comparing with what we have got before. Now let's compare this equation B with the equation A, which we have got in the last week. So this is the equation A, which we got, TEF minus TEB, 2 times IF1 square multiplied by R2 by S, minus 2 times IB1 square R2 dash by 2 minus S. Now if you observe A and B, both are exactly equal. So that's the exciting thing, that, and that's also the beauty of this concept, because we have started with a single phase machine and we have imagined that our system to have an imaginary winding, that is auxiliary winding, and we have made the current flowing through the auxiliary winding zero, so that it will mimic the behavior of our single exact equivalent circuit. So if you see, the both are equal, and if you want to say in other words, if you want to speak in other words, now here the equation B which we are seeing, this is the torque of our new circuit. This is the exact equivalent circuit. Now the moment when we divided all the parameters of the circuit by a parameter 2, that means all the resistance, all the impedances were half, what happened to my current? My current became twice. So if my current became twice, my power will also get twice. Now that's why there is no need to multiply the secondary term here, because in this equation we have multiplied our torque and power equations by 2, because that is a two-phase machine concept which we are talking about there. But here there is no need to multiply any two factor, because it is also in single phase induction machine current circuit, but also when we have half the impedances, the current factor is already doubled, making the power already doubled. That's why we are getting the both equations same, even though we have not multiplied by 2 here. So there is no need to multiply any factor 2 here. Anyhow, this is only a single phase machine here. Now, yeah, this particular circuit is the single phase induction machine equivalent circuit, which is running on a single winding, that is only one main winding. Now, yeah, so usually what we usually write here is the torque expression. We will replace the 2 times the IF1 square with I1 and I2. We can also write like this: TE is equals to I1 square, I1 square multiplied by R2 dash by 2, 2s minus I2 square multiplied by R2 dash by 2 minus S. Okay. Now this is the dramatic torque, and here I1 is equals to 2 times of IS, and I2 is equals to 2 times of IB. Now see, if we want to solve this particular equivalent circuit further, what we can do, now here we are seeing this equivalent circuit, right, this particular thing. So here there is a two parallel branches. If we can able to find an equivalent impedance of it, like let's say this forward field's impedance, we can say ZF, and backward field is ZB, I mean RF plus JXF, and RB, if we can find the equivalent of it, RB plus JXB, and we can replace our circuit with like that, and I will quickly draw this little part, and here we will start our forward field equivalent impedance, and this is the backward field equivalent impedance, and then we will have our supply. This is R1 X1 RF XF RB XB VM. And now if you see this equivalent these two parallel branches in the equivalent circuit, the resistance part is only one term, R2 dash by 2s and R2 dash by 2 minus s. The equivalent will only affect the reactance part, but not the resistance part. So here RF and RB values are directly those two only, R2 dash by 2s and R2 dash by 2 minus s. Okay, yeah. So now if we simplify like it, now my torque will be even simplified. See now, and now I have made an equivalent circuit. So whatever current flowing through will pass in series. So IF only will pass through this, and also IM only pass through this part of the circuit as well. Now my this equation will further simplify it into. Now I can just write Im square instead of finding the forward current flowing through the resistance part. Now here Im is already flowing through both resistances. Im square into Rf plus Im square into Rb. Now this is the final dot expression where here the Rf and Rb are the resistance equivalents. Only just it's same as the resistance part. So yeah. Now, yeah, equation one or equation two, anything we can take. The resistance part may be affected if we take the equivalent, and we will see what uh, if we given some problems on it, we can find the equivalent impedance of that particular branch, and we can just calculate the IM current from the source, and that's where the total current flowing through the circuit. Now, we also said that we can actually verify the circuit. Now, when we started the discussion for our single phase induction motor, we started with some notations, and we have drawn some conclusions about our single phase induction motor, that our single phase induction motor does not have any starting torque, right? Because only there is a one winding and there is no two forces to auxiliary with each other. No two forces are in quadrature with each other, and that's where we found the need to introduce another winding. So if we have to check whether this equivalent circuit is exact or not, we can verify this equivalent circuit at the starting. So if it is at the starting, we know we should not get any torque, right? Okay. Now see, now the torque equation is I square R2 by 2s minus I square R2 dash by 2 minus s. Okay, R2 dash by, sorry, something is missing there. R2 dash, okay, so here it is R2 dash by 2 into 2 minus s. Okay, I have forgotten that. It is R2 dash by 2 into 2 minus s. Okay, now taking verifying equivalent circuit at starting. At starting, we know S is equals to 1. Now, what will my torque expression would become if it's starting? Just substitute S is equals to 1 here. I1 square by R2 dash by 2 minus I2 square uh, R2 dash by 2. Uh, but if you see, at the starting, let's say this R2 dash by 2 and R2 dash by 2 are there, and here I1 square and I2 square are there. I1 square is 2IF and I2 is equals to 2IB. Now, since this uh, these two resistances are same now, R2 dash by 2 and R2 dash by 2. Now, if we see this R2 dash by 2 and X2 dash by 2 and R2 dash by 2 and X2 dash by 2, these two are exactly similar, and also it is JXM by 2 and this is JXM by 2. So these two are similar parallel branches. So the current flowing through this branch will exactly equal to the current flowing through this branch. So 2IF will be equals to 2IB. What I meant to say is I1 will be equals to IB, because 2IF and 2IB are exactly same now, because R2 dash resistance parts of both circuits are exactly same. Now if I1 is equals to I2, then what will happen? These two will get cancelled and we get the zero starting torque. Now this is what also verifies our circuit, where we can say that at the starting we don't get the enough torque for our single phase induction motor, and that is also verified from our equivalent circuit. Now if it is in a running condition, we can say if, here running condition means slip is not equals to 0. There exists some slip between 0 to 1, 0 to 1. Now if you substitute that, I1 square into R2 dash by 2s, and same expression minus I2 square into R2 dash by 2 into 2 minus s. Now these two are not equal and it is not equals to 0, so there exists some torque, that is running torque. So that's what these are the two main points which we have concluded last week. A single phase induction motor doesn't have starting torque, but it has a running torque. So that's the verification our equivalent circuit also satisfies it. So yeah, this is the part which we wanted to complete last week. So with this, the single phase equivalent, single phase induction machine concept is completed now. With this, we can close the single phase machine discussion. Now we will step into this week's discussion, which is a new discussion we will be doing this week, and this is about the single phase. Sorry, this is about the another AC machine, which is a synchronous machine. So yeah, synchronous machine is another kind of AC machine which we wanted to discuss in this course. Uh, Synchronous machine is also another simple machine to analyze. It's very simpler in equivalent circuit modeling, phasor diagrams. Everything is simple, but the thing is you have to be sure with the concept. If you are sure with the concepts and all, it's very simple to understand. Uh, Synchronous machine is comparatively easier to analyze when we see the induction machine, RMF, rotating magnetic field, and all. But the concept should be clear. Now, yeah, let's. Okay, synchronous machine. See, like in case of three-phase induction motor, not single phase. In the case of three-phase induction motor, which we have discussed for the last few weeks, when we energize the stator in our machine, my rotor will anyhow doesn't require any supply there. Only my stator needs the energizing supply. My rotor would pick up the speed. It will run at some speed an hour that is less than synchronous speed, but it will not be requiring any additional supply for the rotor. So that's why we call three-phase induction motor as a singly excited motor. Three-phase induction machine is a singly excited machine. Now, whatever, because we are just giving the supply to our stator. Now, my rotor also needs some magnetizing current. It will draw some magnetizing current. My machine will draw some magnetizing current, not rotor. So, whatever magnetizing current is needed for my motor, if it is an induction machine, it will draw the entire magnetizing current from the supply itself. So that is XM, which we are talking about, the parallel branch XM. So the current passing through the XM is IM, which we call it as a magnetizing current that is needed to set up the flux. Now, whatever magnetizing current is needed, my induction machine will draw it from the supply itself, and then the motor will run subsequently. So that's the concept we have discussed. Now, and one more thing in induction machine we know, that is we know the voltage equation of our induction machine, right? Per phase voltage equation, if you see, it is 4.44 frequency, flux per pole, and kW window factor, and turns. Now, I have given supply to my machine. That means my supply voltage is fixed, and since my supply is fixed and my supply frequency is also fixed, whether it's 50 hertz in India or 60 hertz outside in US, now it is fixed. Now, since V phase and frequency both are fixed, this particular phi will also get fixed now, because apart from this, our other parameters are constants only. Now, my flux per pole is fixed. So if my flux is fixed, my net magnetic field intensity, that is also fixed. The magnetic field is also fixed. So this is what we have discussed in the induction machine. The moment we fix the supply frequency and also the supply voltage, The level of my flux set up in the machine is fixed. As my flux per pole is fixed, eventually my B net will also remains constant no matter whatever load my machine is running at. That means it's from no load to full load, B net is also fixed. But in synchronous machine, it is different from whatever induction machine is happening because uh, even though I fix my supply voltage and also my frequency in the induction motor, my air gap flux, the flux, it will change. It we see how it will change by doing something else. We can change the air gap flux. We cannot say that as soon as my voltage and frequency are fixed, my air gap flux will be fixed. No, it's not in the synchronous machine. We will see what it is. Now, two more points, important points about a synchronous machine is it's not a singly excited machine, but it's a doubly excited machine. So the name itself says that giving supply to just the stator is not enough for a synchronous machine to run. Our rotor will also need some kind of supply. So it can this particular doubly excited it is valid for both motor operation and also the generator operation. But the important thing is my synchronous machine is not a singly excited machine. Giving supply just to stator will not make our motor rotate. And there is no concept of RMF in the rotor circuit, and there is no concept of induced EMF there. It's not an induction machine anymore. And my rotor does need some another excitation along with the stator. That's why we are calling our synchronous machine as a doubly excited machine. Now, if you see the construction of a synchronous machine, it's simple and almost very simple. If you see, it's very easier to understand because we will have a stator in a synchronous machine that will be housing the three-phase winding. It's a three-phase synchronous machine. So my three-phase winding would be excuse me, on the stator, it will have a three-phased balanced distributed winding, whatever distributed or concentrated. Now, my rotor, if you see, okay, I'm drawing the stator on which we will have the three-phase winding. Okay, like this, you will have. Now, let's say this is the stator winding. So this one should house our stator winding. If it's a double layer winding, you will have two here like this. So like that, you can place all the stator three-phase winding in the stator slots. Now in this, in between, we will have a rotor. So rotor can have different structures. So let's say if our rotor is having cylindrical rotor structure. Uh, let's say this is some slots I have drawn for the rotor, and rotor can be cylindrical or any other type, but here we have drawn a cylindrical structure which has some slots and some teeth you can see here. So, but the winding which is present on this rotor is not a three-phase winding. It's just a very simple winding. So this one, it's the stator three-phase balanced winding, and here, let's say this here and this here. This is the rotor winding. It's not three-phase. See, yeah, it's not a three-phase winding as I said. It's just a very normal winding. You can just take a wire and you take a wire and wound around like it, like just from the figure. If you want to see, just take wire. You just bring it and bring it from here, and you bring it from here, and you bring it from here, like that. You can just wound it around the rotor slots. It doesn't matter because it's not a three-phase winding we require here. Now, But what supply we will be giving to this rotor? So I will just write here. It's a stator and it's rotor. So the kind of supply we will be giving to our rotor is DC excitation. So this is what we called as a field coil, and the excitation we give to our DC rotor is a DC supply. We call it as a DC excitation. So it's look like as follows. Let's say this is my stator. I draw it like this because it's a three-phase winding. It will my stator will have a three-phase winding. Now my this is like a rotor, and let's say I have just drawn it like this such that let's imagine this is a cross and this is like a dot. I mean I have wound it like this, and current is going through and coming out like this. I mean like this it is having some kind of winding like this. Okay, now if you see, uh, if we can able to pass my DC current through that of rotor winding such that I can get cross here and also the dot here, my how would be how would be my lines of force using thumb rule we can say that. So here it is the current going and here it is current going up. Now it will be pointing towards my thumb. So in this way it will my lines of force will be in this way, right? And this is the stator winding. Okay, here we are seeing the rotor is as a cylindrical type, or else usually we can also have another type of rotor. This is okay, let's write it at the bottom. Cylindrical rotor. We can also go for another kind of rotor like a projected rotor. So which will something look like this. So see, if this is a stator will remain same, of course. Now here also the winding will be like this. So if it is cross here, it's a dot here. Now again using thumb rule, same thing. So here it will be like this, right? Okay. Now this kind of projected rotor, which is having two poles here. Usually we can use four poles also. If you want to see a four poles projected one, it will look like this. Like this it will have. Here we have two poles. We call it as a salient pole. Salient pole rotor. It is cylindrical rotor, synchronous machine. Salient pole rotor, synchronous machine. Now saliency means like having this kind of projections. That's a word mean the saliency. Okay. Here we call this winding on the rotor as a field winding because we are giving a DC excitation. It sets up the field flux in the machine, and the winding present on the stator, that's a stator three-phase winding. In terms of synchronous machine, we also call it as a armature winding, three-phase armature winding. Now stator winding, we call it as armature winding. Rotor winding, we call it as a field winding. Now, one thing we have to note here is whenever you see the ratings of a machine and compare to the induction machines, so this my rating of the synchronous machine here could be very large when we compare to the induction motor. So my single phase induction motor would be even lower. Right. So single phase induction motor, let's say in the order of watts only, like 600 watts or 400 watts, anything, even smaller. But my three phase induction machine would be of in the order of kilowatts, 100 kilowatt motor, even 250 kilowatt. Even we have solved the problems also. We have seen some different kilowatt hours of induction machine. Now, Okay, we have seen 200, 300 kilowatt induction machines, but this synchronous machine which we have, it can go up to megawatts. The megawatts of, if you see some industries and all, you can see a megawatts of rated motors there. Now, why is this difference? Why can't we have a megawatt rated induction machine, but why are we having only synchronous machines in the megawatts? So, any idea? So, why are we having a megawatts in synchronous machine but not in three phase machine? So, this is because of the biggest disadvantage what induction machines are having. Someone saying, I can't hear you. Someone's talking. Anil, you want to say something? Okay, chat box. Doubly excited? No. S- Doubly excited is only, you can say it as a disadvantage. You have to give an additional supply. You have to provide a battery bank for it. Okay. Okay. Yeah. So we already discussed. Okay. I've got some other requirement of insulation. No load current will increase. Yeah. No load current. Very low power factor. Okay. Why are all this coming? Like, what's the reason behind it? Why there is no load current is increased? Why it is very low power factor? That's it. Because of one reason it is happening. Insulation, it is required for both induction and synchronous as well. If you are going for high volts, you need to have a even higher insulation for high voltage protection. So the important quality that separates the induction from the synchronous machine is induction machine draws magnetizing current from the supply, right? Now, the more the rating of the motor, induction motor, the higher the magnetizing current drawn by it. So, if you see, like someone said the no load current will be there. Yes, when you see at the light load condition, even the no load condition, the kind of magnetizing current it draws is lagging. If it is a no load, of course, it's completely lagging. It's like an inductor, 90 degrees lag you will observe. And if it is a light load condition, it will still be lagging. That's why not exactly 90, but some angle. That's why you will always say induction motor will always have a lagging power factor, never leading or never, not even unity power factor. It's always supply the lagging loads and always have a lagging power factor, but that's okay. But the discussion is why can't we go for higher ratings? So when we are going for higher ratings of induction machine, the amount of magnetizing current drawn by the machine is also higher. But even that's not the problem. Okay, let it draw magnetizing current. Let it set up flux required flux in the core. The problem is the magnetizing current, whatever amount the induction machine needs, it draws from the supply itself. Now, why would supply should supply main supply along with the magnetizing current to the machine? So that's a loss. Now, when you are drawing such high magnetizing current from the source, it's always a disadvantage. So this particular characteristic of drawing the magnetizing current from the supply makes the motor to have a very low power factor. It's not even not that very low, but it does have a very low power factor when compared to other machines. Now, particularly during light load condition, as I said, now this magnetizing current will make the power factor almost 90 degrees lag. That is zero power factor. But during light load condition, it's very poor power factor. Now, anyone why anyone wants a machine to work at a very low power factor, especially at high ratings, right? So if it is a large size induction machine, there will be a large magnetizing current drawn by it. Now people don't go for high rated induction machines for a three phase system. Now when in case of a synchronous machine, if you see my excitation, whatever I'm giving, it's completely DC, right? My secondary excitation which I'm giving to the rotor winding, is a DC. It's a completely DC. It is free from any alternating supply. Now it won't be drawing any lagging or leading loads. It will not draw any lagging magnetizing current, and I just have to give some battery bank. I just have to keep a DC supply or a battery bank. Any some kind of way we have to find to give a DC supply to my rotor. That's it. There is no need of any like no need to take care of the magnetizing current in the machine. Now we know if my stator carries a three-phase balanced current, that we know that. So this is the stator here. You can see stator. Now we know whenever a stator, whenever a three-phase balanced winding is carrying a three-phase balanced current, what will happen? Rotating magnetic field will be generated. So that is what we call stator field here, because my stator is housing the winding of three phase. Now okay, this particular three phase, okay, we have given a three phase supply to this, and balanced three phase winding, and three phase balanced current flows to the winding, and what will happen? Rotating magnetic field, RMF, will be produced, and now it will move in this direction or in this direction based on the phase sequence ABC, SEB, RYB, RBY, and always leading to lagging. The field will move. Of course, that's separate. That's different discussion. But it generates a rotating magnetic field, and it moves with the speed of synchronous speed. That is whatever is supply. If it is a 50 Hz supply, and if it's a four-pole machine, we can say the NS, that is 2F by P with RPS. That is the speed of my synchronous field that is generated as a rotating magnetic field in the stator. Right now, what about the rotor here? Now, what supply we have given to the rotor? Here we have given a DC supply to the rotor. Okay. Now here my rotor is excited with a DC, and what will happen to my DC? Well, RMF will also be produced in the rotor, because see, in order to run my motor, in order to rotate my rotor, there should be two fields, that is rotor magnetic field, stator magnetic field. And if we saw it in the induction machine concept, both fields should rotate with the NS. Both rotor magnetic field and stator magnetic field should have the same speed, NS and NS. The mechanical speed of the rotor might be less, that is NR. Based on the slip, it will change, but the fields of those two should be same. So that's what we discussed in the last few weeks about the induction machine. Now see, if we are giving a DC supply to our rotor, and it is a stationary field, it's not alternating. We won't be generating a rotating field. It's a stationary field. RMF is produced? No. So Fs is rotating with NS, RMF is produced. Now FR, of course, there is a field produced, because the rotor winding is there. We have flown some current into it through the DC supply, but it is not rotating magnetic field. It is a stationary field. Now, yeah, now see, if we want to rotate, like if let's say, forget about rotating, even if we want to operate this machine as a motor, we know that my stator is carrying the RMF, and my DC, my rotor is carrying the DC field. Now, what should I do to rotate it, to make the motor run? Will it produce torque in this condition? No, definitely it won't produce, because see, we know that for the production of a steady electromagnetic torque, the relative speed between stator and rotor field must be zero. It means that if both speeds are both fields are rotating with the speed of ns, let's say this is of stator and this is of a uh, rotor. Now with respect to a stationary observer, now let's say here is the observer. He is observing the speed of these two. With respect to a stationary observer, those two are relative speed between those two should be zero. Exactly, if both speeds are having the same speed, a stationary observer should say, okay, I can see two fields, stator field and rotor field. They are moving at the same speed. Then only the angle between these two will be constant. So then only they can produce the steady state torque. That's what a stationary observer would say. Now, looking at this, all the conditions which I have discussed in the synchronous machine, what we can conclude now. Let's say I have a synchronous machine. I have given AC supply and I have given a DC supply to my router, and I want to run it as a motor. Will it run? No. So another conclusion, the same way which we have developed conclusions for a synchronous, induction machine. Here also we have some. We conclude that looking at the synchronous machine, the thing I can conclude is it has no starting torque, right? Definitely, it doesn't have a starting torque. So it's just a stationary field in the rotor. It's not rotating with ns. It's not even rotating with some speed. It's just ns. Now, what to do? What I will do is it's interesting here. So this is a very simple idea anyone can do. See, in my stator, I have generated rotating. So this direction anyway, it will depend on the say phase sequence, but I'm just assuming it to be an anti-clockwise direction. If it is rotating in this direction, if it is fs, and here I have, let's say this is my rotor winding, and I have flown idc current through it, and they generated an fr here. It is not rotating. Now what we should do, very simple technique anyone can see by it and tell is, okay, you have told some condition, both fields should rotate at the same speed ns. Now here the speed is equals to 0 currently, and here it is ns. What someone can do is, if by some way, if by some mechanism, if I can able to rotate my rotor physically from the outside, the rotor is there, I'm rotating it with my hand. Okay, just go and rotate. Just I'm rotating it so that it will the speed will go till ns. Okay, fine. Now I have made my rotor also a rotor field rotor physically rotate such that my stator field and rotor field will have the same speed. Okay. Now the both are in the same direction. I have rotated my rotor in the anti-clockwise direction as same as the stator field. Now, therefore, I will have to find some way which can make the rotor rotate physically from outside. Mechanically, we have to do something or do something such that my rotor field will also rotate. It's not stationary field anymore. Therefore, what I can conclude is, for a synchronous machine to work, my rotor must also run at a ms speed, which is the same speed of the stator RMF. So that's what we have drawn the conclusion. IMF no starting torque. Another conclusion is, to make synchronous machine run, rotate rotor such that speed of rotor field is same as stator rotating magnetic field. Here it is, speed is ns here. That's what the another conclusion which we can make from directly discussing the concept of synchronous machine, right? Now, what will be the power and torque? Any machine, what is important? We discuss the concept of the machine, how it will rotate, and then we discuss the construction of the machine, what is stator, what is rotor, where is the windings placed, what is the supply given to them, and then once we place it, and we will see the equivalent circuit of the machine, and we will see the torque expression, power expression. That's what the basic analysis of a machine is. Okay, now for the synchronous machine, I told you this phasor diagram and equal circuit is very simple for a synchronous machine. Now let's see what are the power and torque expressions for a synchronous motor. First, we will take motor operation. So generator operation will be discussed in the another TA session. But just now we will see how a synchronous machine can be operated as a motor. So motor means what? There is no generation within the machine. So my machine should take supply from the mains. That is, it will take some voltage, and that will be supplied to my machine, and physically I have to anyhow rotate my rotor that is already there. But okay, motor operation is you have to take the supply from this mains. But what if it is a generator? If it is a generator, you will generate some excitation. Voltage will be generated from the generator, synchronous generator, and that we will give to the bus. That means you have to supply some loads which are connected to the bus. That's the generator operation. Here we are looking at the motor operation. So to answer the questions of power and torque expressions for a synchronous motor operation, we will have to first draw the phasor diagram. Once we draw the phasor diagram, and then we can easily find the torque expression for it. Now it's very simple discussion. Okay, phasor diagram of synchronous motor. Okay, see, my synchronous motor will have some excitation voltage. That is, this is synchronous motor, and this is excitation voltage EF. We call it as an EF, and it will have some impedance. It will have some resistance and also reactance. We call it as a synchronous impedance. That is ZS, and at the end we will just have a supply. It will be at some voltage. Let's say if we take our voltage to be at reference at 0 degrees. Now EF will be at some degrees, lagging or leading. We will see later how the angle will be. But yeah, if you take a reference, it will be at some angle. So the angle between V and EF, we call it as a delta, that is load angle. And the angle between uh, supply voltage and the current flowing through the circuit. So see, it's a motor. Motor means it will draw the current from the mains. So the direction of current is very important. So this current armature, the current flowing through the stator armature winding, we call it as an IA. Now the angle between voltage and current, we know that is the power factor angle, theta, or sometimes we use beta also, anything, the theta or beta. Now ZS is RS plus XS, everything is same. This is how a equal circuit of a synchronous motor would look like. Here the impedance is ZS. My bus voltage is V at an angle 0. Now since it's a motor, it is drawing power from the source. Now if you assume that's the direction of IA, it means that it is a motor operation, and that will be IF, you can see here. Now let my motor is drawing a lagging power factor load. That means my current is lagging the supply voltage. I mean, whatever supplying the lagging load means by load where it is connected. So this since it's a motor, so here there is some prime mover, and my motor has to rotate that load. So whatever it is here, it is the lagging load. Now let's say my motor also draws some lagging current from the machine. So how would my current everything would look like? Now what is the equation of a motor here? So you see, this is the excitation voltage, this is the total supply voltage. My EF, that is a total voltage, EF will be V minus IA into ZS, right? That means if you write ZS as RS plus RA plus XS, IARS minus JIA into XS. Okay. Now we are supplying to a lagging load here, and if we draw the phasor diagram, we will take V at an angle 0, means let's take V as a reference for now. V, this is at an angle 0, and yeah, it is supplying to a lagging load. Now my IA will be lagging. So this is the theta or beta, whatever it is, the power factor angle theta. Now there is a V here and we know Ia. Now we are trying to calculate the EF voltage here. Now we have to subtract the resistance drop and also the impedance drop from the voltage. Now Ia RS has no phase, so Ia RS drop will be in the same phase as the Ia. So here it will be Ia RS this in this way. Now if we take the same that is Ia RS drop, now we can do it like this, right? Okay. Now it is Ia RA and we have drawn a line parallel to it. This is IARA, but here it is minus IARA. Minus IARA, will draw it in this direction. Minus IARA. Now we have to draw IAXS. It's multiplied by J. It will be 90 degrees from the IA. If it's the IA, it's here, and it will be 90 degrees from here. So if we do a from here IA, you will have the IAXS. So it will be like this. IA, this is J IAXS, but it's minus J IAXS. So it will be in this direction. IAXS. Now V, it is V minus IARA minus IAXS. The resultant will be my excitation voltage EF. Now, if it is at a 0 degrees, the angle between will be delta. That's what we said. See now EF will be at an angle of minus delta, right? If it's at 0, it will be minus delta because it's always below the VA. Now this is the condition for a motor. If you see any phasor diagram of a synchronous motor, my EF will always be below the V only. That's how it is. EF is V minus IARS and IAXS drop. If we subtract the resistance drop and as well as the impedance drop, we will get the excitation voltage here. So yeah, that's it. Now, if a motor draws lagging current, that's what we are seeing here. Now we see the length of EF here will always be less than V. Now see this length of EF, when you compare it will be with the length of V, it will always be less than the voltage from the supply. Now what we are trying to come up what we are trying to discuss is excitation voltage, right? Excitation voltage EF, and we have a resultant. Now excitation voltage EF, it is for the rotor. We know that it is rotor field, and whatever resultant field we are getting, that is for the V, is equals to resultant. Now my resultant V is more than my excitation. So it means that the amount of excitation you have given is less when compared to the resultant. Now, since my excitation is less, we can say my motor is under excited. Excitation is less. You have to you are not giving enough excitation to the motor. So we call this kind of condition of this motor as a under excited condition. Now the direction of rotation which we already discussed is that if it's in the anti-clockwise direction, my speed is not that direction, my torque will also be, electromagnetic torque will also be that direction. Now under this condition, if you look at the power expression, we have to talk in terms of complex power drawn by the motor. Now this is the complex power which is being delivered by the supply. Usually they call it as both. Drawn by the motor is also same as complex power delivered by the source. Now see, as we call the complex power is apparent power, that is V I star. So this is the complex term we are getting, Vi star. It's a very well-known formula. Now for Vi star. Now for this, let's draw a simple diagram for it. That's which we have drawn in the previous slide. So this is the impedance, and here it is the voltage V, and this is F at an angle of minus delta, and V at an angle of 0, and this is the Zs at an angle of beta. This beta is nothing but the power factor angle theta or beta, which we can see what notation we can follow anything. So VIA star, it is drawing IA current from the supply. My motor is drawing from it. Now, what is the IA expression here? IA is V minus EF at an angle of minus delta divided by the impedance, that is Zs beta. So V at an angle 0 minus EF at an angle minus delta. So these are a very simple arithmetic calculations, but very useful for the numerical problems. So yeah, synchronous machine is very comparatively easier to analyze, but you have to be thorough with the concept. So it will be easy to derive the equations, very simple. Okay, now we have got this. Now if you simplify it, VF V by Zs at an angle of minus beta minus EF by Zs at an angle of minus delta minus beta. So this is what IA is. Now what I need? IA star. IA star means complex conjugate. Take the negative of the angle here. V by Zs at an angle of beta minus EF by Zs at an angle of delta plus beta. So minus will be cancelled out from both. Now what is the formula for S complex power here? You have to just multiply voltage to it. If you multiply voltage, so this is for a single phase. If it's a three-phase machine, you have to multiply with the 3, and we will see that later, but you have seeing it for the one phase. Now V square multiplied divided by Zs at an angle of beta minus V into EF divided by Zs at an angle of delta plus beta. Okay, this is the complex power, apparent power. Now if I want the real power, that is P, what will be? It will be, see, S is equals to what? P plus JQ. That means like it is VI, right? It will be, you can write it as VI cos theta plus J VI sin theta. So the cos part will be the real power and the sin part will be the reactive power. Yeah. Now take the cos part of it. Yeah, Anil has talked about that excitation current drop in the supply. Yeah. Sorry, I missed your message, Anil. Yeah, that's precisely the reason. So what's the time? Okay. Now, yeah, that's a now if you take the cos part of it, now my real power would be V squared by Zs cos beta minus V into EF by Zs cos delta plus beta. Now this is the real power that will be drawn by the motor. Now usually the condition in a synchronous machine is the resistance within the circuit. Here we have seen the Zs is equals to R plus jXs, right? Rs plus jXs. This resistance is usually very small. So usually we neglect the resistance in a synchronous machine. It just if we see if Ra is neglected, because reason I'm writing Xs is usually very greater than the armature resistance. Now my Zs at an angle beta is nothing but jXs, Xs at an angle of 90 degrees. Now you have to replace that in the power formula. V squared by Xs, it is cos beta, it is cos 90 now, minus V into EF by Xs cos delta plus beta, delta plus 90. Now what it will be? It's cos 90 is 0 and cos 90 plus theta will be minus sin theta. Now it will be V into EF by Xs sin delta. So this is very useful formula. Even in the power systems, you can see this formula is very uh, yeah. This is very popular formula. It's all after neglecting the resistance part of a circuit. Yeah, that's it. Like this, let's at the last thing. Let's see a simple comparison to the generator and the motor operation. You will you can understand it better. Okay, so let's first try to draw the equivalent circuit for the generator. So first try to draw the motor, because we already discussed the motor EF, and there will be excess. I'm neglecting the resistance here. It's V, and this is the resultant voltage, and this is the excitation voltage, and current is drawn here, and this is excess, and this is the EF. Now, what is the motor equation? EF will be V minus J IA excess. Okay, this is clear. Now, let's say it is supplying the lagging power factor, and later we will see for leading also. Now, okay, now lagging power factor means we just saw the phasor diagram for it. If it is a V, it is IA, and it is beta or theta. Don't get confused. Anything theta or beta is fine, and it is IA, and there is no IA RA drop anymore. It is just IA excess. It is positive IA excess, and negative IA excess would be in this fashion, minus. Now the resultant V minus IA excess will be EF. Now see, EF will always be below V. This is delta, so we can write it as minus delta. And since the length of EF will always be less than EF V, we call it as a under excited. Now let's see the difference between the lagging and leading here. Now see, this is V. Now let's say it is applying the leading power factor load, so the IA will come up. Now my current is leading, so this is beta, and okay, now I have to take the excess drop, subtract IA, and a perpendicular to here, this is the Ji excess, and should then negate it, and we should subtract it from the V, and it will be like in this fashion, minus Ji excess. Now V minus IA should give you the E here, so EF. Now in both the lag and lead cases, you can observe that your EF will always be below EF, right? It is delta. It is always minus delta. Now, if it is a V at an angle, if V is reference, then EF will be at an angle of minus delta. Now, if your EF is at a 0, now V should be at an angle of delta. It's anything, it's just representationally, whatever you are taking as a reference. If your excitation voltage is reference, it we know that in a motor condition, EF will always be below V. Now, if EF is itself at a 0, now V would be somewhere around, above it. That's why V will be delta. So anything is fine. But the important point is you should make note that EF will always be below V in motor condition. We will see for generator, then only you can get a clear differentiation. Anyhow, now if you see here, the length of EF is bigger when compared to the length of V. Here your excitation is more. Here excitation is length of EF is higher than the length of resultant. So you have enough excitation, not enough even if it's a more excited condition. So you call it as it is under excited, it is over excited. Okay, now if you see the similar kind of analysis for a generator, I will have excitation voltage EF, you will have excess here, and you will have mains here. Now what it will my generator do? It will supply to the machine. So current direction is in this condition here. IA is actually supplying to the bus here. So let's say it is a bus voltage. Now it is supplying to it. Okay. Now the equation of generator would be EF is equals to V plus J IA excess. Right. That's obvious. EF would be summation of supply voltage with the drop. Now let's say it is supplying to the lagging power factor. Now I take V as a reference, and it's a lagging power factor. this would remain, the concept is same. IA, it's a power factor angle IA. Okay, now what I have to do, V plus IA axis. IA axis will be perpendicular to this one, and parallel line to this. This is IA axis J, and V plus IA axis would be my excitation voltage EF. Now, what we have observed in this lagging power factor, you see the EF is above V now. Now, this is the delta. Now, EF would be at a delta when V is a zero. That's a generator condition. Now, another point, the length of EF when compared to the length of V is bigger here. Now, what is this condition? It is over excited when supplying a lagging power factor. Now the same condition, I will quickly do it for leading. Now this is V, leading power factor. IA would be leading, and this is beta. And I have to add the IA axis, and IA axis would be this one, and this one. IA axis would come here, J, IA axis, and E would be V plus J axis. This is my EF. Then this is my delta. Now again, from both lagging and leading, for a generator case, we can see that my excitation voltage is on top of the my supply mains bus voltage V. And another thing about the leading power factor is the length of the EF excitation voltage is lesser when compared to the length of the resultant V. Now what we can say, it is under excited. Now, just compare all these four cases of generator, motor for both lagging and leading cases. It's very simple. It's the equation. First, you have to draw the equivalent circuit. You have to derive the voltage equation. It's simple. In generator, EF is more because EF is actually generated voltage and it will supply the bus. And in the motor, EF would be the excitation voltage, but it is drawing current from the supply. So V minus drop will give the excitation voltage in case of motor. Once you get the voltage equation, you take the lagging load, leading load. Based on that, IA position would change. The important point you have to observe is, what is my motor condition here? Is it under excited or over excited? And what is the position of EF? Is it below my V or is it above my V? Based on that, so if by just looking at the phasor diagram without even you can close the equivalent circuit on the top, and just looking at the phasor diagram, you could be able to tell whether it is a motor or generator. So these four diagrams and also the equations are very important, but at the same time very easy and also very important for your problems during your gate concepts. So just if it is synchronous machine, it's all based on these questions only. And another part is there, if it is synchronous generator, you will have the synchronization concept. That those things we will discuss in the next coming TA session. But in this discussion, please pay attention to the notations of current flowing in the circuit and how we are arriving at the excitation voltage, and what are the angles between notations, supply voltage, resultant voltage and current, and excitation voltage, and the power equations, what is the complex power, and what is reference, what is what, and anything you can take. So if you see here, the input in case of motor, the input power, you can say that this is the input and this is the output because current is flowing here. So the three phase input power is 3 VI star. The current is same VIA star. And if you see the output condition, if you want to get the output, here it is the voltage and you know the current, it will be 3 EIA star. This complex I am talking about. If you want to real power, then from that you can just substitute E and F. So the easy way would be, whatever power you are calculating, take that as a reference, because if you take this, V would be V at an angle 0 and then E would be at an angle of minus delta. If you are calculating output power, take E as a reference and your V would be at an angle of delta. Everything is same, but it's just for a convenience purpose, you can take like that. Okay, yeah. So those are the concepts which we wanted to discuss for today. And the time is already 5:20 and we have not more than 40 minutes to discuss the problems in this week. So yeah, please listen. Please discuss to. Please participate in this next discussion now. We will be solving some problems on the synchronous machines, and please be interactive in this next 40 minutes so that we will have a good discussion, and also it will help you solve for the assignment problems. So please take a pen and paper along with me, and also your calculators. Bring those calculators out so that we will solve some problems. Okay. Yeah, very basic problems, and also some interesting problems are from synchronous motor concept we will see, and let's proceed with the discussion. So yeah, let's read the question. Read the question along with me. We were given with a three-phase 440 volts line-to-line delta connected synchronous motor, and we are given with the synchronous impedance Zs is equals to 1 plus J5. So here we can see the resistance is 5 times less than the excess, but resistance still is very high. It's not even 5 times, it's very less than excess. Okay, anyway, we are provided with the per phase impedance and also the excitation voltage, that is 550 volts line to line. Okay. Now, rotational losses will be 1 kilowatt. Those are constant rotational losses. Okay, fine. Now, what it is? What is it? So we have to estimate the line current under maximum input power condition. So again, we have to estimate the line current. That's okay. We just have to. It's very simple. If you can able to draw the circuit and also draw the expression for the line current, it's well and done. It's easy. But we are provided with the condition here. So it is that you have to estimate the current at that instant where your input power should be maximum. Now let's first write the expression for the input power. Then only we can see when it will be maximum, when it will be minimum. Okay. Okay. Now, so let's solve the problem with me. So what is the input power? This is the input power we need. Now, in order to get the real power input, let's first calculate the apparent power. Okay, S is equals to 3 V I A star. So this is what the phase current, 3 V phase I phase. Anyhow, first we have to calculate. In order to calculate this one, we need to calculate this phase current, right? IA star. Now, how can we get IA star? To get IA star, we need to calculate IA first. So how can we get IA? It is a motor or generator. It is a motor. Just draw the equivalent circuit. This V, and it's a motor, and it's EF. And since it's a input power condition, this let's take this as a 0, and this at an angle of minus delta that we know, and RS and JXS, and current will be this IA. Okay, yeah. From this, can anyone tell me the formula for IA? It's very simple. Now V at an angle of 0 minus E at an angle of minus delta divided by Z at an angle of theta. Theta is what the power factor angle, right? Now if we further simplify it, V by Z at an angle of minus theta minus E by Z at an angle of minus delta minus theta. This is what IA is. Okay, now what is my IA star? V by Z at an angle of theta minus E by Z at an angle of delta plus theta. Okay. Now let's arrive at the real power equation first. That is this part first, and then we will see when it will be maximum. Okay. Just substitute this IA here. Now S is equals to 3V V by Z at an angle of theta minus E by Z at an angle of delta plus theta. Now multiplying it, V square by Z at an angle of theta EV by Z at an angle of delta plus theta. Here V is at an angle of delta 0. That's the point of taking it at an angle of 0. No point of giving it here. S. Now let's tell me what is the formula for real power input. It is the cos part, 3 v square by z cos theta minus ev by z cos delta plus theta. Okay. Now if you see cos, this is the input power and we want it to be maximum. Now if you see there is a two terms are here. One term is getting subtracted from another term. If we want to make this term as maximum, this particular term should be maximum and this particular term should be as minimum as possible. That's when your power would be maximum then. So this is the highest value and we are subtracting very minimum value from it, then only it will be maximum. But what we have control on in this expression, on what factors we have control on, because v is given, z is given, theta is also fixed, because 1 plus 5j is my impedance. If my z is equals to 1 plus 5j, what is my z at an angle of beta, I mean theta here. So z will be root of 1 square plus 5 square, that is the magnitude of z. And see, I'm writing it here. Magnitude of z is 1 square plus 5 square. It is equals to root 26. And theta is equals to tan inverse of beta, tan inverse of imaginary part by real part. Tan inverse of 5. How much is tan inverse of 5? Okay, change it to radian mode, complex shift mode. Yeah, it's radian in degrees and shift tan inverse of 5. It's 78.69. So yeah, this term is fixed now. Now we have to make this term as minimum as possible. So when so it means minus of this one. So this cos term, if it is as minimum as possible, then only it will be maximum. So when will be cos will be maximum? When it will be the negative maximum? Right, cos will be negative maximum when this angle will be equal to 180, because then only the value of cos term will be minus 1, that is a negative maximum. If it is negative minus 1, then it will be plus here, then the total expression will be maximum. So the condition to get a maximum power will be delta plus theta should be equal to 180 degree, then only you will get a maximum. Now substituting that, calculate the input power maximum. Right, it is 3 into v square by z cos theta, and it will be minus 1 minus plus ev by z. Now this is your maximum uh, maximum power, maximum input power condition. So this is what you got. Now what is the question we have asked now? The question we have asked is we have to estimate the line current under this maximum power input condition. Okay, and under this condition we have to get the maximum power. So let's get the expression for the line current now. Okay. Now if you see the expression for the line current, IA line is equals to, if we know the phase current, IA is phase, IA will be multiplied by root 3. Okay, what is phase current now? We already wrote the formula, V at an angle minus E at an angle of minus delta divided by Z at an angle of theta, that is the power factor angle. Now at this maximum power input condition, we know that delta plus theta is equals to 180. Now delta will be 180 minus theta. We will be substituting this in this delta, root 3 into what is the angle of V? It is a 440 volts. Here we can see 440 volts line to line. V minus 550, that is also line to line at an angle of theta. Minus delta will be theta minus 180 divided by z. Z we have to calculate z at an angle of theta. So z will be under root of 26 at an angle of theta is equal to 78.69. So yeah, theta is also, here you can substitute 78.69. So someone calculate the line current for me and also tell me. I am also calculating, so please calculate it. Okay. Multiplied by root 3 240 minus 450 divided by z 26 at an angle of theta. Theta is what? This one. Root 3 into 240 minus 550 at an angle. Theta is how much? 78.69 minus 180 divided by z at an angle of theta. Z is equal to under root 26. 5.099 at an angle. Theta will be again 78.69. Okay, this is what. I'm not missing anything. Okay, the line current which we are getting here is 190.3 at an angle of minus 152.93 amps. Okay, this is the magnitude, this is the angle. Okay, now let's calculate. This is the line current. So the next question is estimate the power factor. Okay, power factor we know that is if it is a P input is equals to root 3 VL IL cos phi. This is the power factor angle. Now, if you want to calculate the cos phi, it's equals to P input max divided by root 3 VL IL. Now, okay, input max we haven't calculated. So this is the input max. You just have to substitute all the values here. V square, that is 440 square by Z, that is under root 26 multiplied by cos theta, cos 78.69 plus EV by Z 550 at an multiplied by V, that is 440 by root 26. So we calculate it and let's see what maximum power you are getting. So 40 multiplied by cos 9 plus okay. Now what I am getting is 164718. 164718.9 watts is equals to It's about 164.7 kilowatts we are getting. Okay. Now we know the line current, we know the input power. It is 164.7 kilowatts divided by root 3 into 440. Sorry, 440 multiplied by, it's 190.3. That angle, it will be coming to this picture because we have to just write the magnitude here. Now when you calculate, still be what's the power factor you are getting? 64.7 to 10 power cube by root 3 into 440 into 190.3. Somehow they're getting more than one. That's wrong. Theta minus 180. Okay. Root 3 times phase current. Okay. Minus V. Okay. Total divided by z angle of theta. Okay. Let's calculate this again. It is okay. 60. $440 minus calculate theta. Theta is 78.69 minus 180. Okay. Now this 440 minus 550 to angle. Okay, 180 minus 78.69 divided by root 26 at an angle 78.69 into root 3. Okay. Now I got the point. So here the current, the calculation which we have made a mistake. Sorry, I made a mistake. So when I take the theta minus 180, I didn't give the bracket, so it multiplied for only theta. So the answer I'm getting is 261.14 at an angle of minus 34.14. Okay, now take this as here, it's not 190.3, it's 261.14. Now if you divide 164 point, now I think it will come correct one, 1.6 and 10 cube divided by root 3 multiplied by 440 multiplied by 261.14. Okay, yeah, it's 0.827. It's the power factor. Okay, now we have to estimate the next shaft power, that is the shaft output power, that is the output useful power we need to estimate under the maximum input power. Now we know the shaft power, that is complete output power, is equals to, if we know the input maximum, that is what the condition is given, if we subtract the all the losses from it, we will get the shaft out power. So what are the losses? There are copper losses and the rotational losses. That's what given in the problem. Now how to calculate the copper loss? But copper loss we will get from total three phase losses multiplied by I phase square multiplied by whatever is the resistance that is present in the circuit. Now I phase we already calculated because we know the line current. We just have to divide it by root 3, and how much is it? 3 multiplied by 261.14 by root 3 whole square multiplied by resistance is 1 plus J5. Resistance part is only 1. Now let's calculate this copper losses. 3 into 261.14 divided by root 3 whole square multiplied by 1. Now 68.194 kilowatt. And when the problem is given, the rotational losses is equals to 1 kilowatt. Now input maximum power is 164.7 kilowatt. Now what will be the output? 164 kilowatt minus 68.194 copper losses minus 1 kilowatt. Now this will give minus 1647 minus 1. So you are getting a 96.5 kilowatt. Okay. So this is the total useful shaft power out of the total input power of 164 kilowatts. Now now we just have to calculate the efficiency. Efficiency in percentage is equals to output power by input power into 100. Now what is the output power? It is 96.5 divided by it is 164.7. Both are in kilowatts multiplied by 100. So if you see 96.5 divided by 164.7, the efficiency is coming out to be 58.5. It is very poor efficiency. It's even not a practical motor. So who will use a synchronous machine motor of 58%? So where is the mistake? What's there is no mistake in the calculations. Everything is correct. But what's the important point you have to note is usually we don't get such kind of low efficiency for any motor of synchronous machine, because here why we are getting, because of the impedance. If we see the impedance resistance is 1 plus J5, usually the resistance is not that much higher. Just because the rotor the synchronous resistance is 1 ohm, that is very much higher when compared to the practical motor resistance. That's why we are getting a low efficiency. So this is not a practical condition. That's what you have to keep in mind. Okay. Now, okay, we have to estimate again the line current, but under the maximum power output condition. So we have done it for the input power. Now the same calculation we have to do it for a maximum power output condition. Now see, so this is the angle, this is EF, and this is the R plus JXS. Now see, this is now my motor is running current. That's all remains same, but we have to see at this output power side. Now we have discussed it. The output power here, if you have to take it input side, you take this as a reference. If it's output side, let's take this as a reference, just for easy convention. Now if it is at a 0, my V would be at an angle of delta. Okay, the output we discussed that S output complex power output will be 3 E IA star, because we know this is IA and this is the output side and this is the excitation voltage. We know it will just be 3 EF IA star. Now this has to be maximum. Now if you do the same kind of analysis here as well, now my IA would be V at an angle delta minus EF at an angle 0 divided by Z at an angle theta. Everything is same. Now IA star would be V by Z at an angle of delta minus theta. Now I am just writing it directly. Theta minus delta minus EF by Z into minus theta. It will be theta only. Right? Now S output is equals to 3 EF should be multiplied to this. 3 V into EF by Z theta minus delta minus EF square divided by Z at an angle theta, right? Now what is the real part from it? 3 VEF by Z cos theta minus delta minus EF square by Z cos theta. Now here we know this term already. EF square by Z we don't have control on because all terms have we know, cos theta we know. But the unknown term is delta here. Now to make it as a maximum, this term needs to be maximum. So this term is anyhow we know it's a value we can't change. Now only we can change this term. So this term should be maximum. So when is the cos term maximum? At 0. Cos 0 is equals to degrees is equals to 1. Now theta minus delta. So to get P output maximum, theta minus delta is equals to 0. That means theta is equals to delta. Right? This is the condition. Now what will be the power expression? 3 VEF by Z. This will be 1 minus EF square by Z cos theta. So let's calculate the power here itself. Again, next, anyhow we have to calculate it. 3 V is how much? V is 440 multiplied by EF is 550 divided by root 26 minus 550 square by root 26 cos theta. Theta is 70. How much is theta? Theta is how much? 78.69. 78.69. Okay, someone calculate it along with me. 40 multiplied by 550 divided by root 26 minus 550 square multiplied by cos 78.69 divided by root 26 multiplied by 3. So it's coming out to be 107.4 kilowatts. 107.4 kilowatts. Okay. So this is what the shaft output maximum power we can get. Okay. Now let's see. Okay. So this question is not completed. We have to find the line current under this condition. Okay. Now to find the line current at this condition, so we know our phase current formula. It is V at an angle of delta minus E at an angle of 0 divided by theta. Now let's calculate this one. 440 at an angle of 78.69 minus 550 at an angle of 0 under root 26 at an angle of theta. How much is this? 440 at an angle of 78.69 minus 550 divided by 5.099 at an angle of 78.69. Okay, now it is 124.2 at an angle of 58.3 amperes. Now we have to calculate the line current, which will be root 3 times of phase multiplied by root 3. You will get 215.15 at an angle of 58.37 degrees amps. Okay. So this is the line current under the maximum power output condition. From the maximum power output condition, we came to know that delta should be exactly equal to theta. So that's where we substituted delta same as the theta. So if you are substituting delta as a theta, that means you are already assuming that it's a maximum output power condition. Okay, next here comes the power factor. So power factor, we know cos phi, if we know the input power, P input divided by root 3 VL IL. Here we don't know the input, but we know the output power maximum. So if we know the output power maximum, input power will be addition of the losses. Here addition will be copper losses plus here addition will be rotational losses. Now the output power maximum what we have calculated it is 107.4. It is kilowatt plus 3, because here if you see this is the line, here it is 3 I phase current 215 by 2 by root 3, that is the 124 by 2 anyway, 3 I square multiplied by R, that is 1. Rotational losses is 1 kilowatt. This is kilowatt and this should be in kilowatts. Now let's calculate this, how much we are getting. 46, this is 46.31 kilowatt, this is plus 1 plus 107.4 kilowatt, 107.4 kilowatt. So we are getting 153.712 kilowatt, 153.712 kilowatt, that is the input power. Now calculate the power factor, 1.712 into 10 cube divided by root 3 into 440 into line current, that is 215.2. Now everyone calculate it. Root 3 into 440 into 215.2. So we're getting 0.93 power factor, 0.9372 power factor. Okay. Now we have to estimate the net shaft power in kilowatt under the. So this is already calculated. Maximum power output is the shaft power. So it's nothing but 107.4 kilowatt. Here we can see this output power is nothing but the shaft power. Okay. Now yeah, again efficiency is percentage is equals to P output by P input multiplied by 100. So P output is how much? 107.4 into 10 cube because of kilowatts, and the input power is 153.712 into 10 cube into 100. So 107.4 kilowatt divided by 153.712 kilowatt will give you an efficiency of 69.87%. Still, it's even very low efficiency for a synchronous machine. So yeah, again, this is because of the 1 ohm resistance that is present in the synchronous impedance of the machine. So practical, it's not very practical. So that's why we're getting very low efficiency. Usually, it's not in that range. It's very even order of 10, 100 less than the reactance of the machine. So yeah, so that's it for the today, and time is also up. It's almost 6 o'clock. Yeah. So yeah, we have covered all the. I feel we have covered all the concepts which I wanted to discuss with you today. So if you have any doubt in today's session, please do ask me.
Sir,
Actually, we
it
have
was
received one
related.
mail that second session is postponed to 7th.
Right, right, right. Your session from 7 to 9 will be on Monday 7 to 9. Yes.
But tomorrow we have to submit assignments.
Okay. Tomorrow, for the questions on the generator part as well, maybe he can discuss. Okay. Second last problem. Which one? Yeah. See, this generator part questions would be also very similar. You can try and try to solve those problems also. It's only same kind of problem will be there in generator part also. So you are asking for this problem. Shaft power. Okay. Yeah, shaft power is nothing but the output power. So we have already assumed the condition for the output maximum shaft output power. It's the same thing. Generator, we have discussed some concepts like right the equivalent circuit and also the power voltage equations and all. So with the same concepts for the motor that is also applicable for the generator, you just have to modify a bit and you can. I don't think it will be that difficult. You just give it a try. I'm sure you'll get it. If you are not getting, you can raise it in the discussion forum. The TA I will also communicate with him to attend those if you are not getting the solutions of that. But I'm sure you will get it. There are 3 to 4 problems in generator. I suppose it will be easy. I want everyone to try it. Yeah. Thank you, Anil. So yeah, no, that's how today session went, and I want to just give a quick recap of today's session. Actually, today we started with the discussion of the last week's session where we have stopped the thread of arriving at the exact equivalent circuit of single phase induction machine, and with that we have arrived at the exact equivalent circuit, and we have calculated the torque equation, and we have seen how the torque equation which we have is valid for all the conditions which we have assumed, which we have drawn at the starting of the single phase induction machine discussion. And then we have started our today's topic of synchronous machines, and we have discussed the construction of synchronous machine and why it is preferred over induction machines when it's a application of higher ratings in order of megawatts. And then we have seen the working of a synchronous machine, how to make it a rotating machine. And then we have seen the phasor diagram of motor and also the equivalent circuit of it. And we have seen the power equation derivation of it, and we also compare it with the generator condition, and we have seen all the 4 cases of lagging, leading loads under excited and over excited conditions. And then we have proceeded with the solving problems on synchronous motor. These are the basic formulas and very easy formulas, and we have just have to note down the given conditions and substitute it. We will get. And yeah, generator also, you please try to solve the generator problems, and similar concept you can get from it. And yeah, so with that